previously nearly about I think 30 lecture hours we spend on finite formulation of various structural problems using lower order elements. We also introduce some higher order elements. In this lecture specifically, I want to concentrate on formulation of one-dimensional heat transfer problems. Basically, we know what is thermal analysis. Thermal analysis, we calculate this temperature and then the relative quantities of interest. The relative quantity of interest might be what is the amount of heat loss or gain or the thermal gradients, the thermal fluxes. Again, this thermal, this heat transfer is taking place by three mechanisms. This you would have studied at our BTech level: heat transfer, conduction by convection, and radiations. In this lecture, I'm going to create conduction and convection. Radiation, you know that it's a non-linear phenomena where the heat flux is proportional to T power 4. So it's non-linear, so we're not going to deal with that. We are going to deal only conduction and convection, both are linear formulation. Types of thermal analysis, steady state and transient thermal analysis. In steady state, that the temperature or the related quantities of interest are, or we calculate at steady state that is independent of time. Whether it's morning or afternoon or evening, the temperature or the heat flux is not going to vary much. So if it is not going very much, then you can assume that the steady state conditions. In the transient thermal analysis, where the temperature distribution and other thermal quantities are that vary over a period of time. For example, you take a sun heating. Morning, you have a temperature, nice temperature will be having, or afternoon will be having around 40 degrees. Okay. So it's also that solidification problem comes under this transient heat transfer problem. Ice melting problem comes under the transient heat transfer problem. But in this lecture, or in this lectures, we are going to concentrate only on steady state thermal analysis. Some of the applications of thermal analysis is aerospace, where we will be interested in temperature at various locations, especially at gas turbine engines. We want to control the performance of the engine. Similarly, automobiles, power generation, metallurgical process, and environmental pollutions. So finite element, as we know, we can apply three methods. You can use it. One is by this direct method, other is by variation method, and weighted decimal method. So the direct method is applicable mainly for simple geometries. The geometry is a very complex one, then you cannot use this direct method. And this variation method and weighted decimal method both are versatile. You also know that variation method is applicable only if functional exists. There are some cases where there is no functional exist. Suppose if a differential equation contain a first order derivative term, then there is no functional exist. So such cases you cannot apply this. There is weighted decimal method concern. There is no innocence restrictions. This is more versatile in nature. You can apply to. We can straight away we can start from differential equation. There is no need for any functional. Let's take a very simple case, heat transfer through a conduction slab wall. One side temperature is T1, other side the temperature is T2. Since in this case we are also assuming that temperature vary in other two directions is negligible, temperature varies only in X direction, then this can be treated as a one-dimensional heat transfer problem. So temperature is T1 and T2. So for the pure conduction, we can apply this Fourier's law of heat conduction where you know that the heat flux is proportional to thermal conductivity and temperature gradient. Want to study at a lower class. That can be applied here. So heat transfer to 1 to 2, that is T1 minus T2, where R is defined as the ratio of del X, where del X is the thickness of the wall, divided by K is the thermal conductivity, A is the cross-sectional area. In some cases, we can take the unit cross-sectional area also. But similarly, for heat transfer 2 to 1, from wall side 2 to 1, T2 minus T1 divided by R1 R2. Okay. So these two equations, these two algebraic equations, we can represent in a very compact matrix format. This turned out to be a Q equal to K into T. Whereas this is called usually a structural problem. We define this as a structural stiffness matrix. Whereas in thermal, that term is not very convenient. People use this called a conduction matrix. Okay. The conduction matrix Ka by del X 1 minus 1 minus 1. This is very similar to our structural. So instead of E, Young's modulus, we are using thermal conductivity K. Only thing we are changing the metal property. A structural problem, metal property, Young's modulus, we use it. Whereas now they are going for thermal conductivity. Right. Next. So what I want to do, I want to follow a very generalized approach. instead of deriving a very specific formula, I want to develop a very general formula, so this can be applied to any of the scalar field problems. Most of the problems in engineering and physics are represented by scalar field problems. That too, these problems are represented by Helmholtz equations. These are second order differential equations. So this equations is applicable for most of the problems in engineering and physics. For example, in the next slide, you could see that the special form of the equation can be represented heat conduction, torsion problem, potential flow, seepage and groundwater flow, electric potential, fluid flow in the acoustics, and many more such problems. So these equations, this kx, ky, and kz, these are the data. For example, the thermal problem, this kx, ky, kz represent this thermal conductivity, where q is going to the heat generation, heat source or heat sink. These are the boundary conditions. Maybe the surfaces I can divide. The first one is boundary condition on surface S1, maybe on S1, on this is on S2, remaining on S3. So this may be applicable or may not be applicable. These are the three possible boundary conditions. Okay. So, this is the special form of Helmholtz equations. If you know element equation for the Helmholtz equations, then that is, if you derive element finite equation for the Helmholtz equation, then you have finite equation for all these problems. So what I am going to do today, I'm going to derive this finite formulation for the general form Helmholtz equation, and then we can tailor it to as per the given problem. Right. So first we will see the variational formulations. In fact, we know what is variational formulation. For variational formulation, start from the functional expression. The functional. So this functional is a differential, the integral form of the differential equation boundary conditions. So this is the corresponding functional for these Helmholtz equations. Okay. This, for stable equilibrium, the functional has to be minimum. It has to be minimized. So minimization, what we do, we differentiate this with respect to the unknown. Unknown will equate to 0. So what is this phi? Phi is the unknown field variable. If it is thermal problem, the phi is going to represent the temperature, or the fluid flow problem, the phi will be your stream function. Or electromagnetic problem, the phi will be representing this magnetic flux. Right? It's a field. Okay, now we need to write this in terms of shear function and nodal values. In order to rewrite this, I'm going to introduce some new matrices. This is called the G matrix. This is called the gradient matrix. This is analogous to the strain. In structural problems, we use a strain. What is strain? du by dx for one dimensional. Okay. So this is similar to here. Here it's a thermal problem. This is going to be the thermal gradient, temperature gradient. Okay. Temperature x direction, y direction, and z directions. This is a gradient matrix. And D is called a metal property matrix. But structural problems, this is Young's modulus. So this is a function of Young's modulus and Mark's ratio. Whereas with thermal problem, this Kx, Ky, Kz are going to represent the thermal conductivity X, Y, and Z directions. Right? If the material is an isotropic material, then Kx, Ky, Kz equal to same. Not going to, the value is not going to change. Okay. Now this equation, this is a quadratic form. Okay, dou phi by dou x. Okay, this one I can rewrite this in terms of G matrix. Okay, G I know G is dou phi by dou x. Dou phi by dou y, dou phi by dou z. This I can write it in this matrix format. So G transpose D G. Okay. This one very compactly written using this matrix notation. G transpose D into G. Okay, so you know how to write. G is I can write this is G transpose into G. Same format I will use this. Right. So now this is in terms of gradient matrix and D. Okay. Plus we have other quantities. Now basically my objective is to I want to write this in terms of nodal unknowns, right? What I'm going to do now? Since finite element consists of meshes. Meshes, there are E number of elements. So what we can do, we can calculate this functional for each element and then just sum it up for all the E number of elements. The summation over E, so that we will have the total functional. We are just introducing this superscript E. That means for each element, we are calculating this functional. See, it may look a big number, but if you can evaluate this integral, it turns out to be a single number. Right? Now, where is phi? What is phi here? Phi is the field variable. It may be temperature, stream function, or it can be a magnetic flux, or it may be permeability. So the field variable at any point, you can write in terms of shape function, nodal values. Right? As usual, you write it. So wherever phi is there, you write in terms of shape function, nodal. This is also applicable for the region, maybe one dimension or two dimension or three dimensions. For example, for a one dimension, you have two nodes, one dimensional two node rod element, linear element. Field variable here is phi1, here it is phi2. So field variable at any point x, I can write it in terms of shape function and node phi1 n1 n2 phi2. Right? Now the same thing, so wherever phi is there, you write in terms of shape function nodal value. Similarly, gradient matrix. What is gradient? It is analogous to strain. So how did you write strain in the structural formulation? We write there epsilon in terms of B and nodal displacement, no? Strain displacement matrix. The same thing here, the gradient matrix. The gradient matrix I want to write in terms of B. The B is called, see, structurally it was called as a strain displacement matrix. In this case, it's only is the one which relates my thermal gradient with temperature vector. Okay, cos are fine. So whenever G is the right terms of B, it multiplied by this nodal vector. Right. So now this equation turns to a very big equation. Same thing. Simple thing is just use some wherever phi is there, you write in terms of n into I, wherever G is there, you write B into phi. And this equation is done to a very big equations in terms of nodal unknowns. Okay. Now, to minimize this, we know that for equilibrium, a stable equilibrium, this I has to be, functional has to be minimum. So for minimization, you differentiate with respect to phi. In fact, with respect to the system degree of freedom. So we have E number of elements. We have E number of elements. The total degree of freedom is IS. We have to with respect to the system degree of freedom and then equate it to 0 so that you can set up the as many number of equations as required. Once you differentiate and then equate it to 0, the equations can be very elegantly expressed in this format k phi minus f equal to 0. Okay. In fact, this k can be written as volume integral B transpose D B phi into dV plus H n transpose n into ds. In fact, this consists of this will not be there. So we have two parts. See, earlier structural, we have written this stuff. Volume integral B transpose D B into dV. The same thing here. Along with it, we have one more term. Surface integral H and transpose n into ds. Right. Suppose if there is thermal problem, we are considering convection, we need to consider this term. Suppose convection is not considered, you are considering only the conduction term alone, then this term will not appear in the equation. Right. The force vector, once you come to the load vector side again we have, this is load vector due to heat generation. Q. There is a thermal problem, Q is representing the heat source or heat sink. Then this is load vector due to heat flux supply. Okay. But this one is load vector due to convection. Okay. This has got three terms. Maybe you just need to note down this sign convention, that's very important. Now let's apply this. Let's apply this for a one-dimensional heat transfer problem. So in a one-dimensional heat transfer problem, so whatever we derive, so this is for general scalar field problem. This is applicable to all these problems. Okay, for example, the torsion problem where kx, ky is 1, kz is 0, q is 2, your free variable phi is stress function theta. Boundary condition theta equal to 0 on the boundaries. And the potential flow problem, then the free variable phi is here stream function. Right? kx, ky again 1, q is 0. The seepage problem, groundwater problem, again this free variable is going to the hydraulic potential. Where k is there, what is the k? K is the hydraulic conductivity. Similarly for electric potential. Electric potential, the k is epsilon. What is epsilon? Epsilon is the permittivity. So this equations, this element equation is applicable for all the scalar field problems. Other thing is you have to tailor it according to the physics. Right. So let's apply this for one-dimensional heat transfer. Okay, so in fact one-dimensional heat transfer, we get only the temperature in other two directions is negligible. Let's consider the heat transfer is only taking place only along this x direction, only one direction. This is the Downing difference equations. K rho square pi by rho square pi by tau x square plus q equal to 0. With the possible boundary conditions. This is the specified temperature. This may be the specified heat flux or specified convection. Now, for this one, this is the element equations. Okay, my k, this is the k, and this is the load vector side. So what I am going to do? Let me derive these equations. Let me derive this. How to obtain this k matrix and this load vector from this general formula. So let's consider a one-dimensional heat transfer like a long fin. Okay, we are considering convection, end convection. We also consider the bulk temperature is phi infinity. We have perimeter convection as well as this end convection. Right? Where K is the thermal conductivity of the material. Right? This one we discretize into using one-dimensional linear elements. In this case, I am just taking three elements. Element number 1, 2, 3, 1, 2, 3, the 4 nodes. Temperature here is phi 1, here it is phi 2, here it is phi 3, phi 4. These are the nodal values. Okay. Now the temperature at any point. Temperature at any point, I can write in terms of shape function and nodal value. We take a typical element. We take a typical one-dimensional thermal rod element. Okay. Node 1, it's a local node. Here material, this is phi 1, here it is phi 2. So the temperature at any point, I can write in terms of shape function and nodal values. Okay. For linear interpolation functions, we have already established the equation. N1 is 1 minus x by L. What is N2? X by L. Already we developed this fact, same thing. Because my shape function depends only on the geometry. It is independent of the physics. Whether it's structural or thermal, shape function remains same. Now what is the corresponding D matrix for a one-dimensional rod element? You just recall that structural, we developed this B matrix. 1 by LE minus 1, 1. So what is the content of B matrix? The content of B matrix is differential coefficients of shape functions. That we already established. Okay. Now, let's apply this. We take the first term. First term in the K matrix. What is the first term in the K matrix? The first term in the K matrix is, this is the conduction term. It's called this the conduction term. I just go for, I'll call this conduction term, this is convection term. Right? So this port conduction, okay, that is volume integral B transpose D B. Just for sake of simplicity, I am just keeping this square brackets. Now, what is the B matrix? This being 1 by LE minus 1 1. D matrix. This is a one-dimensional rod. So since the one-dimensional rod, we have only thermal conductivity only x direction. This is 1 by LE minus 1 1. This is a uniform rod. Cross-section area is a constant. Area is a constant. Length is dx. Since it's a constant term, you can take it outside of the integral. Take outside integral. Then you multiply it. What you will get? You will get A by LE 1 minus 1 minus 1 1. This is very similar to our structural stiffness matrix. Instead of Young's modulus, we have thermal conductivity for 12. Now let's take the second term, conduction term. Let's take conduction term. It is surface integral H and transpose N into ds. Again here, the convection possible. Convection can be a perimeter convection. It can be eddy convection also. Possible. Let us take the perimeter convection first. Then we will go to end convection. So what is the end matrix for one-dimensional rod element? N1, N2, N1, N2, right? Now this becomes H into N1, N2, N1, N2. What is ds? ds is the surface area. So that is perimeter multiplied by dx. Okay. Suppose it's a taper rod. Let's take a taper pin. Possible. Special cases. The taper pin, P is no more constant, P will be a function of x. It is also possible that we can have exponentially varying cross section. Possible. You use the corresponding function for P, right? But right for our case, perimeter is constant. Now this becomes, I can take HP outside. This multiplied by N1 square, N1, N2, again N2, N1, N2 square, dx. Now we integrate this each of the term in the matrices individually. To integrate this, we can make use of the factorial formula, what I told you already. So what is this factorial formula? N1, N2, dx. What is this? Alpha factorial, beta factorial, alpha plus beta plus 1 factorial into L. See? Over a domain. So this one, first case is N1, N2, dx. But 1 factorial divided by, sorry, first case is N1 square. I mean N2 power 0. So 1 factorial, sorry, 2 factorial, 0 factorial, 2 plus 0 plus 1 factorial into L. What you will get? L by 3. Second one, integral of N1, N2, dx. So this one, 1 factorial, 1 factorial, 1 plus 1 plus 1 factorial into L. So you will get L by 6, right? Now, this becomes, the convention term becomes HP. I can take L by 6 outside. HP L by 6, 2, 1, 1, 2. Right? Now, again, this conduction are going to consider for end conduction also. It's also possible that conduction may take the end of the finish. We are considering end convection. So for convection type, for N convection, again H, N transpose, N into ds. Now for N convection at node 2, this is taking place at node 2, second node. Okay, second node. See at node number 2, H N transpose S N1 square, N1 N2, N2 N1, N2 square, or ds. See at node number 2, what is the integral of ds? Okay, at node number 2, what is N1 and N2? N1 is 0. Node number N1 is 0, N2 is 1. Okay, so wherever N1 and this becomes 0, 0, 1. What is the integral of ds? A2. Okay, A2 is A. This becomes H, A, 0, 0, 0, 1. Right. Here we consider the convection, convection at node number 2. It is also possible that convection at node 1. This node number 1. Let's make a small change here. 1, 0, 0, 0. So according to the convection, you will make a small change here. Right. Now the total K. So the stiffness matrix. Now the stiffness matrix, this K matrix consists of conduction term. What is conduction term? K, A by L, 1, minus 1, minus 1, 1, plus perimeter convection. What is perimeter convection? X, P, L by 6, 2, 1, 1, 2. Then end convection at node 2. This H, A, 0, 0, 0, 1. So this is my K matrix. Okay. Now let's go to the load vector side. Once in the load vector side, first let us consider the internal heat generation. It is also possible. Inside the element, but this Q is analogous to body force, it's structural body force. This is the one which is distributed throughout the entire volume. But this term load vector due to heat source given by this volume integral Q N transpose into d. So this Q N1 N2 since for a constant cross sectional area, this is A into dx. Now this Q is a constant term. Really A is a constant, I can take it outside the integral. This becomes integral of N1 dx, integral of N2 dx. Okay, so this becomes Q A L by 2 L by 2. This we know, integral N1 dx. Okay, so this becomes Q A L by 2 1 1. In fact, say this body force is represented as equivalent nodal values. But the total heat source Q multiplied by volume. The total heat load equally shared between two nodes, node 1 and node 2. So this is QA L by 2, QA L by 2. Right? This is very similar to the body force, where we have rho A L by 2, rho A L by 2, no? Same thing here. Okay. Next, let's go for heat flux term. Heat flux supply. Again, this heat flux can be supplied either on the perimeter or can be supplied at the end is also possible. So heat flux supplied on the perimeter. Say the heat flux supplied on the perimeter, around the perimeter. First case, this becomes Q. Heat flux supplied on the perimeter. This is Q N transpose ds. Now this Q N transpose is N1 N2. What is the surface area? Ds. This is perimeter multiplied by dx. Let's just take a small distance. Okay. This QP is a constant, I can take it outside the integral. This is the integral of N1 dx, integral of N2 dx. Then once you evaluate, this becomes QEL. L by 2 you can take it outside. L by 2 you can take it outside. 1, 1. Even the surface load. The surface load, the corresponding point load. The corresponding point load is QPL by 2, QPL by 2. Like equivalent modal loads. This is similar to the traction load, what we studied as structural traction load. Now, E-flex also can be supplied at either node 1 or node 2, N node, possible. E-flex supplied at node, let's consider the E-flex supplied at node 2. It's E-flex supplied at node 2. Then this becomes same thing. At node number 2, N1 is 0, N2 is 1, is it? N1 is 0, N2 is 1. N1 is 0, N2 is 1. Then we will have, what is surface area? Surface area, integral of surface area, node number 2 is cross-sectional area. Cross-sectional area, node number that is A2. In fact, my A2 is equal to A. With the uniform cross-sectional area, this becomes Q A 0 1. But this is E-flex supplied at node 2. So E-flex supplied at node 1 1 0. Let's make the change accordingly. Now let's go for convection term. The convection, in fact, this convection term H phi infinity, in fact phi infinity is the bulk temperature, surrounding temperature. So this H phi infinity is equal to Q here. This is the same thing, the same format. Again, this convection can be either on the perimeter or convection can also take place on the end node, possible. Either at node 1 or node 2 is also possible. So I'm going to consider the convection is taking place at node number 2. At node number 2. Then this becomes, the convection term becomes convection load vector is H. Wherever Q is there, replace H into phi infinity. Right? Similar way. H into phi infinity by 2. That is, surface convection is represented by equivalent point load 1 1 plus end convection H EL H into A 0 1. This is for convection term. So this is the overall one. This is the overall expression for element equation or one-dimensional element form considering convection and convections. That is perimetric convection and anti-convection. Similar E-flex supplied around the perimeter, E-flex supplied at the end node 2. So you have to be very careful in while solving problems. You have to make some changes in the here, depending on the case, whether convection is node 1 or node 2. This is applicable for convection at node 2. It is node 1, make 1 0 0 0. Similarly here also make 1 0 1 0. Right? Now let's take one numerical. Any doubt on that? Any questions on that? Have you understood?
Sir.
Yes,
sir.
Right. Let's take a very simple problem. Calculate the temperature distribution along a field using a finite approach. Thermal conductivity is given. K is given 3 watts per centimeter degree Celsius. Convective temperature is given as 0.1 watts per centimeter square per degree Celsius. But the bulk temperature is given as 20 degree. Celsius. Bulk temperature is surrounding temperature, air temperature. The cross section of the fin is a rectangular fin. Height is 1 centimeter, the width is 0.4 centimeter. The first step is discretization. To discretize this geometry into elements, I'm going to use a linear element. I'm dividing this fin, 8 cm fin into 4 elements. Actually, in this case, we divided it equal intervals or equal lengths. It need not be. Actually, in practice, you have to use a fine mesh here. Maybe you have to use force plus here. Wherever the temperature gradient is more, you go for a fine mesh. Maybe in practice here we will go for fine mesh here you can go for the force one. In this case, for sake of simplicity, for academic interest, I am just using the uniform length. Each node length is 2 cm, 2 cm, 2 and 2. Okay, now let's calculate the other parameters. For other parameters, this one, K by L. Calculate the conductivity is given, area is given, area is a rectangle. L is given, L is 2 cm, H value is given, perimeter you can calculate, circumference you can calculate. Okay. All the data are given. Right. Of course, in this case, there is no heat flux applied. Also, there is no heat generation. We have only perimeter convection and convection. Okay. So, we need to calculate. Let's calculate these things separately. And let's bring it, use it here. In this one, you just see that first, all the 4 elements, all this element number 1, 2, 3, 4 experiences perimeter convection. Element number 4, in addition to perimeter convection, there is also a end convection. Okay, so K1, K2, K3, same. You can calculate for this K1, K2, K3 are same because we have perimeter convection term, convection is same. Element number 4. Along with this, we have end convection term. What is end convection? It is HA. HA 0, 0, 1. Okay, you need to add this. HA 0, 0, 0, 1. You want to add this one. Right? So we got this K1, K2, K3. Similarly for K4. Once you come to load vector side, we are considering only the element number 1, 2, 3. We have only perimeter convection. What is the formula for perimeter convection? Load vector due to perimeter convection. H by infinity T L by 2 1 1. Okay, we calculate this for element number 1, 2, 3. The fourth element, element number 4. This is same for element number 1. Element 1, 2, and 3 is same. Element number 4, we have perimeter convection along with we have end convection. H by infinite end convection at node to second node. H by infinite A 0, 1. Okay, this is for F4, fourth element. So we calculate this element system matrix and element load vector as usual. You assemble this K1, K2, K3. I get a stiffness matrix K. Assemble 5. Assembling this K1, K2, K3, K4. Right? Similarly, load vector also. You can assemble F1, F2, F3 and F4. Once assemble it, you will get this final equation. This is the assembled one. K multiplied by load vector, that is nodal vectors, temperature equal to load vector. Okay. Now this one, apply the boundary. What is the boundary condition? The boundary condition is that T1 equal to 80 degrees Celsius. T1 equal to 80 degrees Celsius. That is Phi1 equal to 80 degrees Celsius. This temperature is given. Okay. Okay. In order to maintain this 80 degrees Celsius, there must be a constant heat flow. Otherwise, you cannot maintain this 80 degrees Celsius. Okay. Let's not go here. We are just adding this Q. Heat source. In order to maintain the 80 is node number 1. There are some cases end temperature may be given. Suppose this temperature is given. Then you have to go for this one. Suppose normally we will give the room temperature. Outside the wall temperature is given. The wall. Now you come to the boundary condition Phi1 equal to 80 degrees Celsius. You add this term. Q is the heat supplied at node 1 to maintain the 80 degrees Celsius. Okay, as usual now, the first degree of freedom is specified. Then eliminate the first row, first column. But you have to be very careful. The specified degree of freedom is non-zero here. If it is non-zero, you have to make changes in the load vector side. What changes you have to make? You multiply the specified value with the removed column and then you subtract it from the load vector side. Okay. So now, the first degree of freedom is specified. You multiply this with the corresponding column. That is the first column. Multiply with it and then you subtract it from the load vector side. You multiply 80 with this thing and then you subtract. This is already eliminated. We need not have to worry about it. Second row, multiply 80 with minus 0.507 and then you subtract it. Minus becomes plus there. Right? Other terms are 0. We need not have to worry about it. Okay. Now using these 4 equations, using this reduced matrix, find out this Phi2, Phi3, Phi4, Phi5. These are the temperature at node 2, 3, 4 and 5. So this is my nodal temperature. Right. So temperature node 1 is 80 degrees, that is specified one. This node number 2, 3, 4, 5. You can see that the temperature far away from the wall, the gradient is almost flat. The variation is small. That is the reason why normally we go for the fine mesh. Near the wall, practice. In practice, here you go for a fine mesh, here you can go for the coarse mesh. So this is one-dimensional heat transfer alloying with film. Now let's go for the second part, the composite part. It is also possible in insulation or in a furnace with multiple layers. Layer 1, 2 and 3. And this can be analyzed by using this one-dimensional heat transfer model. Let's take a problem with the 2 wall. Okay. In fact, this side temperature is given as minus 5 degrees Celsius. This is the corresponding convective heat transfer coefficient by H value is given. Other side is atmosphere, open to the atmosphere. That temperature is 20 degrees Celsius. The corresponding K value, this K value for inner layer is 0.2. This for outer wall, it is 0.06 watt per centimeter degree Celsius. The thickness is, this is 2 centimeter and this is 5 centimeter. You will ask to find out the temperature distribution across this wall. Right? We can model this. So this can be modeled with one linear element, one thermal rod. This wall can be modeled as another minimum. Minimum we need 2 elements, but if you want, you can take more number of elements also. At least we need 2 elements. Right? Now, what are the loads involved here? There is no heat generation, no heat flux supply. Convection, also only end convection. End convection supplied at end convection at node 1. Okay. So what you have to calculate is K1 and K2. How to calculate K1 and K2? See for element number 1. See for element number 1. Element 1. K given by K1, A1, L1, 1, minus 1, minus 1, 1. plus element number 1 your convection term. Anti-convection at node 1. For H, A, let's say 1, 0, 0, 0. Right, the derivation we did for anti-convection at node 2. That's why we put 1 here now. 1, 0, 0, 0. Now we calculate for K1. What is K2? Element number 2. K2 we have only conduction term. There is no convection term. K2, A2, L2, 1, minus 1, minus 1, 1. Calculate K1 and K2. You assemble these two. You assemble these two. Next load vector side. And load vector element number 1. We have only anti-convection at node 1. This is H. Find infinity. This area. Line by is node 1, 1, 0. Okay, anti-convection. Element number 2. No convection. Element number 2. 0, 0. Okay, calculate K1, K2, F1, F2. Assemble it as usual. You can assemble it. Got K1, K2. This load. This is element number 1. Once you assemble it, it will be a 3 by 3 matrix. The K matrix multiply with nodal temperatures pi 1, pi 2, pi 3 equal to the load vector. Now, what is the boundary condition in this case? This water temperature is specified. Water temperature is specified as 20 degrees Celsius. That means my T3 is specified. T3 is specified as 20 degrees Celsius. In order to maintain the 20 degrees Celsius, there must be a constant heat flow. So this Q is the unknown heat flux supplied to maintain this 20 degrees Celsius. Now we can remove this third row, third column. Remove third row and third column. The remaining things you can solve the remaining equation. Reduce. What is the reduced equation? 0.2 minus 0.1 minus 0.1 0.112 multiplying with pi 1 pi 2. Then you have to be very careful that this side you have to make some modification. Anywhere removing this column. So you multiply what is specified value 20 multiplied with 0. You know there is no need to make any changes there. So minus 0.5. Minus 0. Okay. Second one, 20 multiplied with minus 0.012. Okay, minus of that. That is 0. Minus will become plus 0.012 multiplied with 20. Right? I will solve for phi 1 and phi 2. These two equations. These are the values. T1, T2 and T3. Right? Let's stop here. Any questions on this? Any questions? It's clear? I suggest you to practice some more problems. This is very important. Right? Thank you.